Hello, and thank you again for joining me. What we're going to be looking at now is we're going to find the volume of a three-dimensional object. In particular, what we're going to have is we're going to have R as the region bounded by the functions f of x equals e to the x squared, y equals 0, x equals 0, and x equals 1. So now in order to find this region, we will have to graph it. But before we get there, I just want to say that what we're going to do in order to make a three-dimensional object is we're going to pull this region out in such a way that when we pull it out, the cross-sectional pieces that are cut into 2 dimensions will end up giving us rectangles. So cross-sections are rectangles, where the height of the rectangle is e to the x squared, and the depth, or how much it comes out, is going to be equal to x. Alright, so now I've drawn a graph of e to the x squared, x equals 1, y equals 0, and x equals 0, at least on the region that we're interested in. And so the region R is precisely just going to be the region bounded by these, which is that region right there. Now, again, we're going to pull this out, so we're going to think that, okay, well, at this point x, what's going to happen is, well, the cross-section is going to be rectangular with a height of y. And now the depth, or how far it comes out, I'm trying to draw this circularly, three-dimensionally, as I'm pulling my finger out. I'm saying that distance should be the same as the distance from the origin, and so then that distance is going to be x. So if we try to draw that on the two-dimensional projection, it's going to look something like that. And so if we bring this down, we get that coming out, it's going to look like that. If we draw this piece over here, notice that it's going to come out by 1, so this is x equals 1, so it's going to come out a full 1. So if I draw that, it's going to look something like that. And now if I connect these, I'm going to end up with a three-dimensional object that looks similar to that. And so if we can imagine that, what's happening is we're starting off really thin. In fact, at x equals 0, we have no depth. And then the depth is going to come out towards us more and more as we continue on. Furthermore, the height's going to get bigger, so it's going to start off this big, and the height's going to go up as we come out. So I'm trying to trace that three-dimensionally so that we can see what that looks like. Alright, now that we have a picture of the object that we're trying to find the volume of, what we're going to do is we're going to, again, like we did last time, cut cross-sections and find volumes of cross-sections. Then we're going to add up all the volumes of cross-sections in order to determine the total volume. So now, as opposed to a two-dimensional cross-section, I'm going to do a three-dimensional cross-section. So I'm going to erase some of this so that I end up just looking at that piece. And what I'm going to have is something that looks like this. So again, we're going to come out x, and go up y, and then I'm going to have some depth to it. So I'm trying to add depth here. So it's going to look something like this. And so what we get is that the three-dimensional cross-section is going to be a rectangular solid. Here the height is the y value, the depth coming out is the x value, and this depth here, or this width here rather, is going to be changing because we want to be able to make this smaller so that we can get better approximations as we go. And so that's going to end up getting infinitesimally small. Therefore, in order to find the volume of the cross-section, what we're going to end up with is, well, since it's a rectangular solid, it's going to be the height times the depth times the width. And so now we need to find each of those. So we're going to start with the width is, well, again, this is what we're letting get infinitesimally small. So this is going to change as we try new examples. So this is my delta of some variable, and if we notice that we're moving left to right, so we're moving in the x direction, so the width is going to be delta x. So we'll put that in over here. Now the width is delta x, the depth we said is how much it's coming out. So if we're at the point x here, we said that the depth is going to be, well, according to our problem, that's just going to be x, so our depth is x. Then our height is going to be that value there, or this value. And so what we saw from the problem was that the height is given by the y equals e to the x squared. So again, our height is e to the x squared. So if we want to find the volume of each of those rectangular solid cross sections, the volume is going to be e to the x squared times x times delta x. Now that we found the volume of each of our cross sections, we can find our total volume by adding these all up. How do we add them all up? Is we integrate. So our total volume is the integral from a to b of e to the x squared times x, and then instead of delta x, it's going to be dx, because we're letting that width get infinitesimally small. In order to continue, then I'm going to find a and b. So what's the smallest x I'm interested in? Well, that's given to me in the problem. Notice that the smallest x is 0. The largest x is given to me as 1. And so what I end up with is the integral from 0 to 1 of e to the x squared times x dx. Therefore, the total volume of that object is just given by that integral. Now, I'm going to leave that integral up to you because we went through a couple examples of integrals in the last two problems. So I would suggest going back and looking over those, getting some more examples with integrals. But we have set this up. We know how to find the volume. We just actually have to finish up integrating to find that given volume. Alright, thank you for joining me for calculus practice. If you'd like to see more problems, you can check out the rest of this playlist available up here. Also, please sure to subscribe to the channel so you can see when we have more of these coming up. In addition to that, you can also check out the link available in the description below to see the written version of each of these problems so that you can pull that up to follow along with the video or to do on your own for extra practice. Thank you and good luck with your studying.